Dear students, today we want to go through the topic electron counting in organometallic compounds. The organometallic compounds, we know that these are the compounds where there is a direct metal to carbon bond. That means there will be a central metal atom which will be connected with a number of ligands through coordinate covalent bond, and the ligands that will be used will must have a carbon atom who will donate its electron pair to the metal atom. So if there is a direct metal to carbon bond, then there will be an organometallic compound formation. Now there are different geometries of organometallic compounds depending on different types of organometallics. Some of them may be square planar compounds, some of may be tetrahedral, octahedral, etc. But whatever be the structure of the element or compound, organometallic compound, you will be having one central metal atom and a number of ligands. Here you will be having, you have seen that this is a carbon monoxide or carbonyl ligand, where the carbon is linked with the metal atom. Here the acetylene is acting as a ligand, where the two carbon atom loosely bound pi electrons are donated to the metal platinum, and so on. So whatever be the structure, there must be some total number of electrons in it, and when we deal with organic compounds or simple covalent compounds, then while studying the stability of those compounds, we studied that the octet rule. That means whenever a particular molecule or particular covalent compound is having 8 electrons for all the elements participating in it, then that will be highly stable. Same is the case with actually organometallics also. If the total number of electrons in the organometallic compound turns out to be 18, then that particular compound is found to be extremely stable. Now, organometallics are, as I said, that these are the compounds where there will be a central metal atom to which a ligand is attached through coordinate covalent bond, and that ligand, the donor atom and that ligand must be a carbon atom to be an organometallic. Now, the metal atom which participates in the formation of an organometallic mostly is the D block metal or the transition metal. Now, D block elements are characterized by actually with the electronic configuration n-1, D 1 to 10, ns2, ns1 to 2, and np0. This means that they have penultimate d orbital with the number of d electrons. They have the s valence s orbital with 1 or 2 electron on. They have a empty p orbital. So if a transition metal having d, s and p orbital want to get stabilized by formation of a compound where all the valence orbitals are filled, then obviously the d orbital can have maximum 10, s orbital 2, p orbital 6. This means that 10 plus 2 plus 6, it will be an 18 electron configuration. So the rule itself is called the 18 electron rule. That means an organometallic will be highly stable if it has 18 number of electrons on the central metal atom, and that electrons will be the total valence electron present on the metal itself, as well as the number of electrons donated to it by the different type of ligands. But though this 18 electron rule actually shows us the stability of a particular compound, but we must be aware of the fact that there are some 16 electron complexes also by the nickel group, nickel, palladium, platinum, or maybe by some cobalt group elements like rhodium 1, iridium 1, platinum, palladium 0, platinum 0, etc., who prefers to go for square planar complexes with 16 electrons. So whether it is 18 electron or 16 electron, it has been found that in depending on the atmosphere, depending on the condition, both the types are extremely stable. But as a general rule, we can say that an organometallic will be stable if and only if it has 18 electrons in it, 18 electrons in it. But there are some exceptions also where the complexes are found to be extremely stable even though they do not have 18 electrons. Now, how to calculate the total number of electrons in a particular organometallic compound? For that, we have to go through two procedures. That means, first of all, we must have a thorough knowledge of the metal participating in the formation of the organometallic compound, and then the ligands who can donate their electrons to the central metal atom. Now, ligands are on the basis of how many electrons they can donate as classified into different categories. There may be one electron donor, just like the hydrogen atom, chlorine, bromine, this atomic halides also are capable of donating one valence electron present in their outermost cell. There may be two electron donor like carbon monoxide, trialkyl phosphine, and the alkenes, and maybe alkynes and carbenes, etc. 3 electron donor may be allyl, carbines, alkynes, etc. 4 electron may be diene molecules. But whatever be the ligand, we must have a thorough knowledge of how many electrons they actually can donate. Now, electron counting provided by breezing ligands also must be taken care of while determining the total number of electrons present in an organometallic compound. So, first of all, we must have a thorough knowledge of the structure that particular complex having, because the same ligand halogen may be attached to a single atom, or it may sometimes act as a breezing ligand also. In that case, the number of electron count by them will be different. So there are actually two different methods. One is called the neutral atom method, and the second one is the ionic method. In the neutral atom method, as the name suggests, each and every one participating in the complex formation must be taken in the neutral form. The metal in the neutral form, suppose we have ferrocene, where the ferrocene molecule can be assumed to have iron in +2 state also, or it may be in iron in 0 state also. If in ferrocene iron is in +2 state, then immediately the 2CP ligand that is attached to it will be called the CP negative. That means both the CP ligands will take one electron to form the cyclopenta dienite ion, CP negative. But if we consider that they are neutral, then immediately iron will be in the 0 state and CP ligand will be in the 0 state. That means it will be a 5 electron donor. So we have two different methods. One is neutral atom method. Here all the metal ligand bonds are considered covalent and ligands are considered to be neutral. No charge is taken into consideration. There may be either 1, 2 or 0 electron to a particular bond. If we have carbon monoxide, ammonia, etc. ligand, and then they will have only their valence electron donating 2 electron each. But halide and hydroxo group, however, do not have octet structure in their neutral state, and then they will be supposed to donate only 1 electron to the system. So these are the procedures. First of all, neutral atom counting method, you will be having the total number of metal electron will be determined from its group. Whatever be the scandium is from 3b. So if we consider a coordination compound of scandium, then it will have 3 electrons in the outermost cell. The scandium 3b, chromium 4, titanium 4b, vanadium 5b. So whatever be their group number, that will be the valence electron present in it. Chromium 6b, manganese 7b. So manganese will have 7 electrons. Then we have to find out the total number of electrons donated by the ligand. Then if the particular complex have a charge, if it is positive, then that much number of charges must be added. If it is negative, it must be subtracted. In that way, the total number of charges, actually the charges are not counted, taken into consideration. All of them are taken as neutral. And neutrally, the total number of metal electron and total number of electron donated by the ligand are taken into consideration. Then the second method is the ionic method, where the metal is supposed to be in an oxidation state, which will be exactly balanced by the number of ligands present. So whatever be the scenario, we have to take the metal in such a way that if the ligand near it can accommodate that number of electrons released by the metal, then only it will go to the ionic state, otherwise not. For example, in ferrocene, we have FeCp whole 2. If iron want to go to +2 oxidation state, then it will have to release 2 electrons. But both the Cp ligand, none of the Cp ligand can take both the electron at one. That means one Cp cannot take 2 electrons. So both the Cp will take one electron released by the iron, and hence we have the compound Fe2 positive but 2 Cp negative. So in the ionic method, actually, we must have the metal in its common or stable oxidation state, and then that ionized electrons will be accumulated by the ligands and they will have their normal oxidation state. So we have to take into account the ligands with their oxidation state, whether it will be definitely negative. For example, if we have chlorine atom Cl, in the neutral method it will donate 1, but in the ionic method chlorine will convert to chloride. Cl plus 1 electron will give you Cl negative. So immediately that chloride will now donate 2 electron. So in ionic method, the metal is taken in its common oxidation state and the ligands will accept the number of electrons they can accept. For example, in oxygen, we can take 2 electrons. So O plus 2 electron, it will immediately give us the oxide ion, O2 negative. So in ionic method, if we have to have oxide as a ligand, then immediately it will donate, its charge will be -2. And these are the ways. So if we consider this particular compound, iridium dibromo methyl monocarbonyl triphenyl phosphine, this particular compound, if we want to find out the total number of electrons, then immediately first of all we have to find out the group number of iridium. Now iridium, cobalt, rhodium, iridium, it is from group 9. So total number of valence electrons in iridium will be 9. The methyl can donate 1 electron. Bromide can donate 1 electron. So there are 2 bromine atoms, 1 methyl group. This will be 1 electron donor, but carbon monoxide will be a 2 electron donor, and phosphine, triphenyl phosphine, will be a 2 electron donor. So if we say this particular compound, what is its electronic, total electron count? 9 from the metal atom. This 2 bromine and 1 methyl, all are 1 electron donor. So total there will be 3. So 3 into 1 plus there are 2 ligands who can donate 2 electron each. So 9 into 3, 3 into 2. Since phosphine, 2 number of diphenyl phosphines are there, so 2 plus 1, 3. There are 3 ligands who can donate 2 electron each. So if we add them, then it will be 18 valence electrons. Same is the case with this compound. Here the Cp ligand is a 5 electron donor because it is pentahapto. And this ligand is 6 electron donor, hexahapto. Chromium is having only 6 electron in its valence shell from its group number 6. So there will be 6 plus 5 from Cp ligand, 6 from arene ligand or benzene ligand. So immediately we will be having 6 plus 5 plus 6. This is a 17 electron compound. Here none of the ligands are considered in their ionic form. Now you see here the bromine can go to Br negative, but in ionic neutral method the bromine is taken as atomic state, not in the ionic state. So another, this is a compound. Here you have a Cp ligand along with carbon monoxide and chlorine. Now if I go for ionic methods, here you see chlorine is taken in negative, Cl negative. Cl negative means it is taken in the ionic form, and iron has to be taken in the 2 positive. Now chlorine can take only 1 electron, Cl negative. Where the other electron will go? That the second electron will go to the Cp ligand. Hence you see that it is Cp negative. So normally Cp can donate 5 electron, but since it is in the ionic form, it will donate 6 electron. Iron in 2 positive, iron in neutrally can give 8 electron, but since it is in the ionic method, we have to take the stable oxidation state, so 2 electron less, and then you will have the ionic method. The previous one was neutral method, and this is another way of calculating the electrons, but here you will be finding the